Uh, Good afternoon to all. Welcome to the 6th week tutorial session of NPTEL course, Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I'm a Ph.D. student from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. In this week, we'll be seeing a few numerical type questions and multiple choice questions based on boiler, different cycles in boiler operations, boiler attachments, superheaters and their arrangements, characteristics of convective and radiative radiant superheaters, use of nozzles in steam power plant, flow analysis of steam in nozzle. So we can move into the question straight away. Look into this problem and try to solve. I'll also try to solve it in a minute. So the question is regarding superheaters. So superheater is actually a device that is used to ensure that anything and everything that enters a turbine is in pure steam or superheated steam case. So this superheater will ensure that the steam that is coming out of the boiler will be much at a higher temperature, much higher temperature compared to the saturation temperature. So there are two types of superheaters. One is radiant superheaters, and the second one is convective superheaters. So the question states why convective and radiant superheaters are connected in series. Is it to increase the efficiency of the turbine section, to attain constant temperature for variable boiler load, to achieve maximum boiler efficiency for variable boiler load, or none of the above? So this has got nothing to do with the turbine section. This is something that happens in the boiler. So does it involve maximum boiler efficiency? Boiler efficiency corresponds to the input, the output to the input that happens in the heat exchanger, boiler heat exchanger. So this has got nothing to do with it. So this. So the first section, the first is wrong, and the third is wrong. So by eliminating these two options, we can get the option 2 is right. But why? The question is why we could attain constant outlet temperature, constant temperature for variable boiler load. For example, this is a radiant heater, radiant superheater, and this is followed by a convective superheater. So these two are two different heat exchangers that takes into properties of radiation and convection separately. So what happens in the case of radiant superheater is that it will absorb a large amount of heat directly from the flame through radiation at lower loads. But in the case of convective superheater, when the load is very high, the amount of flue gases that will be flowing through that increases the convective heat transfer in that region. When at a higher load region, this convective superheater can be used to control the heat of the outgoing steam. So basically what happens is if I plot the load or steam generated generation rate in boiler to the superheater outlet temperature, so what we could see is that in the case of a radiative superheater, at when the load is less, uh, at lower loads, it since it is placed very much close to the boiler flame, the heat transfer will be happening through radiation, and the outlet temperature, superheater outlet temperature, can be maintained as such at a higher temperature. But once the load increases, uh, what happens is that the flue gases in the boiler increases, and then the radiation actually will be hindered by the presence of these flue gases, and the outlet temperature that could be maintained due to this radiative superheater will reduce. But the vice versa happens in the case of convective superheater. So when the load or the steam generation rate in the boiler is less, the flue gas formation will be less and the convection heat transfer coefficient will be less. But as and when the load increases, the heat transfer coefficient due to the convective heat transfer coefficient increases, convective heat transfer coefficient increases, and the superheated outlet temperature will be increasing. So instead of using a single one, we will use both of them combined so that we can get a lot more feasible or kind of better regulation of the temperature of we can get a better steam outlet temperature out of the superheater when we use them both combined. So this one operates better at the radiative superheater operates better at lower steam load, while the convective superheater operates better at a higher load. So when we use a convective and radiator in series, we can get a stable superheater outlet temperature in all the cases of the steam generated. So the answer is option 2. Look into the question 2, and I'll also try to solve it in a minute. Okay, the question is regarding superheater. Which of the following statement is or are correct related to the superheater? It is a type of boiler accessory. It increases the quality of steam. It is a type of boiler mounting. It controls the steam flow rate. So the main difference that we have to identify whether it is an accessory or a mounting. So a boiler mounting is actually fittings that are attached to control and monitor the boiler's performance. So this is fittings to regulate the boiler performance. However, the boiler accessory are the fittings that are used to improve the efficiency of boiler. So basically, superheater is kind of an accessory that improves the efficiency of the boiler. What happens is that we are actually heating it uh, to ensure that the steam that enters the turbine is at a higher temperature. So this ensures that if I try to draw it on a TS diagram. So what happens is this region is superheating. So we increase the temperature of heat addition, and in that process, the efficiency increases. So it essentially means that this is it's a boiler accessory and not a boiler mounting. We are not going to control the performance based on this one. It controls the steam flow rate. No, it's not right. Will it increase the quality of the steam? Yes. If take a case when the superheating is not there, it will be directly coming like this at a lower quality. So once it gets superheated, it increases the quality of the steam. So option 1 and 2 are right. Look into the third problem. Which of the following statements is or are related to the water tube boiler? In a water tube boiler, flue gases pass through the tube and water surrounds the tube. Cochrane boiler is a water tube boiler. Babcock and Wilcox boiler is a water tube boiler. In water tube boiler, water flows through the tube and flue gases surround the tube. Look into it. I'll also try to solve it in a minute. The question is which of the following statement is or are correct related to the water tube boiler? In water tube boiler, flue gases pass through the tube and water surrounds the tube. The last option is the exact opposite of this, where the water flows through the tube and flue gases surround the tube. So the answer is 4. So the water tube boilers are the ones where the water flows through the tube, converts into steam by taking heat from the flue gases which flows surrounding the tube. So there are two types of boilers. One is called the Cochrane boiler, and the second one is Babcock-Wilcox boiler. So we need to check which out of the two is a water tube boiler. So water tube boiler means that water flows through the tube and flue gas is outside. So Cochrane boiler is not that one. Cochrane boiler is something where the uh, flue gases flow through the tube and water will be surrounding it. Babcock-Wilcox boiler is is a type of water tube boiler where the water flows through the tube. So basically, what we could try to see is that if this is a water tube, it will be heated by the flue gases and the flame. So this is a type of Babcock-Wilcox model boiler. But in the case of a Cochrane boiler, the whole thing changes. There, uh, the flue gases flow through flue gases flow through the tubes. So this is the boiler, and here the flue gases Flue gases flow through like this. Gases. A portion of those flows into the tubes. So this flue gas will be heating up the water which is present outside. So this is flue gas Fg. Fg means flue gas. This is water. So this is a type of uh, flue gas which flows through the tube. So this is called Cochrane boiler. So the right answers are option 3 and 4. Going to the fourth problem. This is a problem related to nozzle. Which of the following assumption is considered for the analysis of flow through nozzle? In the case of a steady flow analysis, we know that it's an isenthalpic process. No, not isenthalpy. There will not be a change in enthalpy in this process. So which out of the four options are right? It's a steady flow process. Yes, we assume like that. The change in potential energy during the flow is negligible. Yeah, we considered that. So whether it's an isentropic flow, yeah, that means it's reversibly adiabatic process. Basically, Q heat transfer will be 0. Steady flow energy d by dt term will be equal to 0. Here delta P E equal to 0. So what it matters is that the velocity at the inlet. If you consider velocity at the inlet is equal to 0, we can write V2 squared by 2g So note in terms of this, we can write in terms of kinetic energy. So the kinetic energy at the exit of m dot v squared would be written as the change in enthalpy. So V2 squared, V2 could be written as V2 could be written as root of 2 2 into H1 minus H2. The unit of this unit will be equal to kilojoule per kilogram. If that is the case, correspondingly, we need to change this unit of this one accordingly. So if you take the unit of this as joule per kilogram, this unit as joule per kilogram, this is kilogram per second, and this particular thing's unit should also be V squared by 2 unit should also be kilogram joule per kilogram. Basically, it is meter per second, meter squared per second squared. This is kilogram meter squared per second squared divided by kilogram. So you'll be getting the same. The in this particular process, what the nozzle what it does is that it accelerates the flow. It will be increasing the velocity kinetic energy at the exit of the of it. So option 1, 2, 3 are right. So all of the above are correct. So looking at the fifth problem, I'll also try to solve within a minute. So the question is, which of the following statement is correct about the working principle of the nozzle? Nozzle increases the kinetic energy of the fluid at the expense of pressure energy. Nozzle increases the kinetic energy of the fluid at the expense of potential energy. Nozzle requires external work input to increase the kinetic energy of the working fluid. None of the above. So it's a reversible adiabatic process. So no heat transfer happens in this process, but there is no work as well. So what happens is that uh, for Mach number less than one, for a subsonic flows, we assume this to be a nozzle. So in this case, what happens? The initial velocity might be zero, somewhere around zero. The final velocity will be very much greater. In this process, uh, we assume that the potential energy will be remain the same at the starting and ending process. So these two are wrong. And what happens? It increases the kinetic energy by using the pressure energy of the system. Basically, pressure energy that is accounted in the enthalpy. So in the previous question, we have seen the change in enthalpy will be used to change the kinetic energy. Enthalpy decreases to increase the kinetic energy. So that is the option. So option one is right. Now we can switch to a numerical problem. So I'll read through it. A boiler plant incorporates an economizer and air preheater generate steams at 40 bar and 300 degrees Celsius with fuel of heating value 33,000 kilojoule per kilogram burned at a rate of 500 kilogram per hour. The temperature of feed water is raised from 40 degrees Celsius to 125 degrees Celsius in the economizer, and the flue gases are cooled at the same temperature from 395 degrees Celsius to 225 degrees Celsius. The flue gases then enter the air preheater, in which the temperature of the combustion air is raised by 75 degrees Celsius. A forced draught fan delivers the air to the air preheater at a pressure of 1.02 bars and a temperature of 60 degrees Celsius with a pressure rise across a fan of 180 millimeter of water. The power input to the fan is 5 kilowatt and it has a mechanical efficiency of 78%. We need to neglect the heat losses and take Cp as 1.01 kilojoule per kilogram Kelvin for flue gases. Calculate the mass flow rate of the air, the temperature of flue gases leaving the plant, mass flow rate of the steam, and the efficiency of the boiler. So I'll read through it. A boiler plant incorporates an economizer and air preheater and generates steam at 40 bar and 300 degrees Celsius. So it has got an economizer, air preheater, uh, and generates steam at 40 bar. So air preheater heats the air before it enters the boiler to reduce the gap between the uh, already boiled, already combusted fuel flue gases and the air. So the difference in temperature can actually result in the reduction in the efficiency of the boiler. So to prevent that, we preheat the incoming air using the flue gases that will be released from the boiler. It generates a steam at 40 bar and 300 degrees Celsius with fuel of heating value 33,000 kilojoule per kilogram. It's burned at 500 kilogram per hour. So that is done. That's a boiler part. The temperature of the water is raised from 40 to 125 in the economizer, and the flue gases are cooled at the same time from 395 degrees Celsius to 25 degrees Celsius. So what it does is that this economizer is used to preheat the water that enters the boiler by making use of the flue gas temperature, flue gas energy. Then the flue after this economizer, flue gas will be used to preheat the air that enters the uh, boiler. So the temperature of the combustion air is raised by 75 degrees Celsius. A forced draw to fan delivers the air to the preheater at a pressure of 1.02 for a bar and a temperature of 16. So incoming air temperature to the preheater is 16 degrees Celsius and 1.02. Then its temperature is raised by 75 degrees Celsius to it will reach 91 degrees Celsius before it goes to the boiler. Pressurized across the fan over 190 millimeter of water. So it uh, so the 1 atmosphere corresponds to 10.3 meters of water at ground level. So this is 180 mm. So it will be 0.18 meters of water. So that will be like 1/6 of the atmospheric pressure that will be raised. So 1.02 plus maybe another 1/6 of atmospheric pressure. That will be somewhere around 1.2 bars. This is some intuition based on the values given. Input to the fan is 5 kilowatt and it has a mechanical efficiency of 78%. So it will give the direct input power to the fan. Neglecting heat losses and taking CP, we need to find the mass flow rate of the air, temperature of the flue gases, leaving the plant, mass flow rate of the steam, and the efficiency of the boiler. So if you consider this to be a boiler, there will be water inlet and there will be air inlet, and boiling happens. Heat input will be there. The water will be preheated by using the flue gases. So this will be making use of the flue gases in the economizer. and this flue gas will be going out of the system, right? So, so the so that will be using the air preheater to heat up the air preheater. So this can be considered to be a schematic of this one. This is water inlet. So this economizer, by tracking the flue gases, first of all, it preheats the water, then in the economizer, then it preheats the air, and before being released to the outside ambient condition. So basically, we will look through the problem. We need to find the mass flow rate of the air first. We will go in a systematic approach in this case. So what we do, we we can write it straight away. So power input to the forced draw to fan, forced draft fan. So that will be equal to flow rate into delta P divided by mechanical efficiency. So the power input to the forced draft fan, delta P, can be written as V delta P divided by mechanical efficiency. So power input device, right? So flow rate could be written as, therefore, this power into mechanical efficiency of the fan divided by delta P. So given the power is 5 into 10 cube, it's 5 kilowatt, and the efficiency is 0.78, and the pressure drop will be is given as 0.18 180 mm of water. So that is basically 0.18 meters of water. So in order to convert that into the standard units of the pressure, so we just uh, multiply it with a G. So this is 0.18 mm. So that is basically H. So we multiplied by the rho and G to get the pressure, actual pressure. So this will be 1000 and this one will be 9.8. That will be in terms of Pascal. Therefore the flow rate is equal to 2.21 meter cube per second. This is because we have it is being mentioned in the problem. The pressure drop in the fan will be equal to 180 mm of water. So in order to get the pressure drop, we just multiply with the density of the water. That's why we have used 1000. But now we need to calculate the mass flow rate of the air. So the m dot air will be equal to this flow rate of the air multiplied by the density of the air. So it's an ideal gas. We have to calculate the density using P by RT. V dot will be the same. We already obtained it 2.21 multiplied by pressure. Incoming air will be at a pressure of 1.02 into 10 power 5 Pascal divided by R is for air it will be 287 joule per kilogram Kelvin. And then the incoming temperature is mentioned as 16 degrees Celsius. So the temperature will be equal to 289 Kelvin. This will give us the density as 1.23 kilogram per kilogram per meter cube. And we get the mass flow rate of the air as 2.72 kilogram per second. That will be the mass flow rate of the air. So that is the first part of the problem. We need to calculate the mass flow rate of the air, and it actually didn't involve any of these other energy balance equations or something. That's directly from the thermodynamics of it. And the second part of the problem, we need to calculate the temperature of the flue gases leaving the plant. So that will actually come down to this actual temperature of the flue gases that leaves the plant. So we need to look into the economizer and the preheater to get that. But preheater is kind of easy because the air going out of the preheated temperature is also given because of a 75 degrees Celsius rise. We know the incoming air. We know the mass flow rate of the air, and we can easily get how much energy is being transferred to the flue gases uh, in the preheater. So the flue gas temperature reduction in the preheater is not mentioned. That's why we have to go for this one, this kind of an approach. So we assume complete combustion of fuel So the mass flow rate of the flue gas m dot gas could be written as m dot air plus m dot fuel. So mass flow rate of air is 2.72 and mass flow rate of the fuel, we have to look into this flow rate. So 500 kg of the fuel is burned. So complete combustion means that we can directly take it as 500 kg per hour, right? So divided by 3600. So that will be giving the mass flow rate of the fuel. So the total flow rate of the flue gas will be 2.855 kilogram per second. Then we use the preheater. So the last module, last component in the system is a preheater, before which the flue gas is rejected to the ambient. So we know the air incoming temperatures. So this is air inlet. So in this case, we know the energy lost by the flue gas will be equal to the energy gained by the air in the preheater. So once this is done, it's a simple energy balance. So mass flow rate of the flue gas will be 2.855 m dot Cp delta T of flue gas will be this one, 2.855 into 1.01 into delta T. So 1.01 is mentioned in the question. So that will be equal to the m dot Cp of delta T of air. So that will be equal to 2.72 into 1.005 into delta T of air gas. So from this one, we can get the delta T of gas. This delta T of air will be equal to 75 degrees Celsius. And everything else is known. Delta T of gas will be equal to 71 degrees Celsius. Therefore, temperature of flue gas leaving the preheater will be equal to 225 minus 71. That will be equal to 154 degrees Celsius. That will be equal to 154 degrees Celsius. Yes. The third option, the third part of the question is we have to determine the mass flow rate of the steam and then the efficiency of the boiler. So mass flow rate of the steam is the water flow rate. So we know everything regarding flue gas right now. We can use the economizer energy balance to get the mass flow rate of the steam. So energy balance in the economizer will be equal to mass flow rate Cp delta T of water will be equal to mass flow rate Cp delta T of gas. So we need to calculate the mass flow rate of the water. That will be this one will be equal to 4 point Cp of water 4.196 and delta T will be equal to 85 degrees Celsius of the water temperature. So that is from this increase in the temperature that is mentioned 40 to 125, that is 85 degrees Celsius. So m dot of flue gas, we have obtained the mass flow rate of the flue gas in the previous mass flow rate of the first 2.855 energy balance, right? Cp will be 1.01 and delta T in the economizer for the flue gas will be from 395 to 225. That will be 170. So therefore, mass flow rate of the water will be given as will be coming as 1.379 kilogram per second. So that will be the mass flow rate the water in this case. And we will try to plot everything in the TS diagram at the end to show how much change in temperature will be there for the flue gas as well as the water temperature rise. Now, the last step is we need to determine the efficiency of the boiler. So, it's equal to total enthalpy or the energy change of water in the boiler to input energy. In this particular case, this will be equal to total enthalpy or energy change of water in the boiler to input energy that is from the calorific value of the fuel. So that will be equal to m dot water into enthalpy change uh, h water out minus h water in. So that will be equal to divided by uh, mass flow rate of the fuel multiplied by calorific value of the fuel. So if you try to plot this whole thing on a TS plane, this will be the Rankine cycle thing. So the boiling happens like this. It makes use of preheated in the economics, it makes use of the energy enthalpy possessed by the flue gases. So the flue gases uh, changes temperature from 395 to 225, and that will be taken up by the water to preheat it. So a portion of that will be the economizer. The flue gas then transfers heat to the air that can be shown in a TS diagram. Uh, So H water out minus H water in. So the H water out will be the water inlet temperature at 45 degrees, saturated liquid water temperature at 40 degrees Celsius. So, so what we could see is that the water temperature is raised from 40 to 125 in the economizer, and the flue gases are cooled at the same time from 395 to 225 degrees Celsius. So this will be the heat transferred that will take into account this as well. The although it is not given in the boiler, a portion of the in order to make it more efficient, this portion will be taken up by the economizer heat. But we can show that that will be the heat transfer to the enthalpy change of the water. So that will be equal to m dot water of H water. So this could be written as 0.2, 0.3, 0.4. H3 minus H2. 0.2 will be saturated water at 48 degrees Celsius. So for the time being, we can assume that the enthalpy of this particular point will be same as that of the saturated liquid at 2, neglecting the subcooling that will be possible at that particular point. And point 3 is 300 degrees Celsius, 40 bar pressure, 300 degrees Celsius, and 40 bar steam. Superheated steam. So the corresponding enthalpy could be obtained from the steam table. H3 will be equal to 2.3 kilojoule per kilogram, and this one will be 167.4 kilojoule per kilogram. So substituting that, m dot water will be 1.379 kilogram per second. We obtained right now 2962.3 minus 167.4 divided by mass flow rate of the fuel will be 500 kilogram per hour divided by 3600 multiplied by calorific value 33,000 kilojoule per kilogram. So we'll get the efficiency as 84%. So this is a problem of boiler energy balance in the economizer and preheater. So the flue gas coming from the boiler will be going through the economizer to preheat the incoming water, and then the remaining enthalpy of the flue gas will be used to preheat the incoming air as well. And before the flue gas is released to the exhaust. So the preheated air in the preheater will be going to the boiler, and the heated water will be going in as well, and the heat input by the burning of the fuel will be the actual energy source. So this preheating will ensure the temperature reduction in the temperature gradient and a better efficiency. So the efficiency of the boiler, we have seen the energy transfer to the water to the burnt, the amount of input energy to the fuel, energy of the fuel in terms of the calorific value. So it's a straightforward problem. By using the energy balance, we have determined the mass flow rate of the air. So air flow rate could have been actually determined straight away using the fan pressure drop. as well as the density of the air for thermodynamic analysis. Flow rate we already know, and we could directly get it from the power required for the input fan as well as the efficiency. Then the second one, temperature of the water leaving, temperature of the flue gas. We have to look at the air preheater. We know everything regarding the air side. So the temperature of the flue gas leaving it can be determined by the energy balance of the preheater. And mass flow rate of steam, similar energy balance in the economizer will give the mass flow rate of the steam, because every other 4 points are known. And finally, the efficiency based on the calorific value, as well as the energy transfer to the water. Another one, another numerical. Just look into it. I'll also try to solve it in a minute. So so this question is regarding a convergent divergent nozzle. Air at 7.8 bar and 180 degrees Celsius expands through it into a space of 1.03 bar. The flow rate of the air is 3.6 kg per second. And assuming isentropic flow throughout and neglecting the inlet velocity, calculate the throat and exit areas of the nozzle. It's a convergent divergent nozzle, so you could expect the Mach number to become equal to 1, and by the time it exits, it will be greater than 1. I'll try to look into it. I'll also try to solve within a minute. This is a so this is a problem of a convergent divergent duct. So we can try to draw that. So the middle point is equal to the choke point, throat point, where the Mach number will be equal to 1. Let this be the 0.0 and this will be 0.1. Incoming air will be at 7.8 degrees Celsius, 7.8 bar and 180 degrees Celsius. and the flow rate is given as 3.6 kg per second. So at the beginning, we can assume that this Mach number will be less than 1. And at the end, we have to determine the velocity. We have to calculate the throat and exit areas in this case. Beg your pardon, there was an issue from my side. Sorry for wasting a bit more time. Yeah, so we can solve it straight away. For the now for the choke point or the throat point, for the throat area, where the Mach number will be equal to 1, we can find the critical pressure ratio where P star divided by PO will be given by the formula 2 by gamma plus 1, since this is a raised to gamma divided by gamma minus 1. So this takes into account the adiabatic isentropic flow. Gamma minus 1. Gamma by gamma minus 1. So from this one, we'll get the value of P star. So that is a choke point pressure. P star will be gamma is equal to 1.4. Using this, P0 will be equal to 7.8 bar. Therefore, P star will be equal to 4.12 bar. And the critical pressure, and similarly, we can find the temperature. T star divided by T0 is equal to 2 by gamma plus 1. So in this one, T star will be equal to T0 will be 180 plus 273. That will be equal to 453 divided by 1.2. It will be 377.5 Kelvin. Straightforward one. And then we'll find the value of the specific volume at the critical point using the equation RT sub PV is equal to RT. So P is equal to PV equal to RT. So RT divided by P star. So that will be equal to 287 into 377.5 divided by 4.12 into 10 power 5 into 10 power 5. That will be equal to 0.260 meter cube per kg. So we know the specific volume at the midpoint as well. Now we need to do a bit more analysis to get the throat area and the exit areas. So we know the velocity at the input point, right? We know the mass flow rate at the input, that is equal to 3.6 kg per second. Now we need to calculate the velocity at the choke point. So that could be written as V star equal to root of gamma RT star. So that will be 1.4 into 287 into 377.5 equal to 389.46 meter per second. So now we know the velocity as well. So now we have to calculate the volume flow rate at the choke point. So that will be equal to Q dot is equal to mass flow rate divided by density or mass flow rate into specific uh, volume at the throat point. That will be equal to, we know 3.6 is the mass flow rate into 0.263. That will give us a volume flow rate. This in terms of meter cube per second. Now using this, we know the velocity, we know the volume flow rate, we can calculate the area at the throat. That will be 3.6 into 0.263 divided by V star. That will be equal to 0.002431 meter squared. So this could be written as 2431 millimeter squared. That is the first part of the problem where we had to calculate the area of the throat. So we had just calculated the pressure, temperature, the specific volume at the throat point. We know the mass flow rate. Using the mass flow rate and the specific volume, we determine the volume flow rate. We have already calculated the velocity at this particular point using this formula. V is equal to root of gamma RT star at the throat point when Mach number is equal to 1. This is the velocity. So then using this, we Mach number equal to 1 in the sense the speed of sound will be equal to the speed of the flow will be equal to speed of sound. So speed of sound could be written as gamma RT star, and thereby we got this velocity at the throat. So using that, we got the area at the throat equal to 2431 millimeter squared. Second, we need to calculate the exit areas of the nozzle. So we know the area at this middle point. Temperature, velocity, all the thing, and the mass flow rate. Just like that, we need to calculate the exit points, temperatures, velocities, and then using the energy balance between the inlet and the exit, we can get the velocity. And to simplify our matters, it is mentioned that inlet velocity is negligible, that is zero. So we use the energy balance, enthalpy balance for the nozzle between the starting point and the ending point to get the velocity at the velocity to get the enthalpy at the exit. Uh, we give it to get the velocity at exit, and since we know the mass flow rate and the volume flow rate, we can actually get the area at the exit. So we try to approach it in such a way. We need to calculate the enthalpies at the first point as well as the last point. So H1, H0 is equal to H1 plus V1 square divided by 2000. Everything in terms of kilojoule per kilogram, that's why divided by 1000 to the velocity squared kinetic energy term. So V1 is equal to root of H0 minus H1 into 2000. So that will be 44.72 into this H0 minus H1. Since this is air, could be written as Cp into T0 minus T1. So this is equal to 44.72 into 1.005 into T0. T0 we have calculated as we know T0 is equal to 180 degrees Celsius. That is 453 Kelvin minus T1. We need to calculate the value of T1. Therefore, just like the previous case where we have used the energy, we have used the this ratio to determine the choke throat point pressures temperatures. We will try to attain and the specific volume we will try to attain this based on the input and in the incoming as well as the outgoing points. So basically T0 by T1 will be equal to T0 by P1 raised to gamma minus 1 divided by gamma. We know the P1, this pressure is equal to 1.03 bar. It's an isentropic process. So basically using the adiabatic equation. So from this one, we'll get T1 will be equal to, this is P0 will be 7.8 bar, 7.8 bar. This will be 1.03 bar, and T0 will be 453 Kelvin. T1 will be equal to 253.9 Kelvin. That will be the exit temperature. So substituting it here, that will be equal to 44.72 into 1.005 into 453 minus 253.9. That will be equal to 634.17 meter per second. So that will be the income velocity at the exit point. Similarly, we should calculate the specific volume at the exit point. So new one could be written as RT1 divided by P1, R287, 250 temperature 253.9 divided by P1 will be 1.03 into 10 power 5. So that will be equal to 0.7075 meter cube per kg. Therefore, area at the exit could be written as volume flow rate divided by area divided by velocity. So that is mass flow rate into specific volume, that is 0.7075 divided by the velocity 634.17. That will be equal to 4016 millimeters squared. So significantly higher than that of the choke area. And the velocity, you could see it is higher than the velocity at the choke area. So even though this is a divergence section, once Mach number will be greater than 1, its velocity increases. It's a continuous nozzle. Though the convergent divergent duct if it is a convergent divergent duct and the incoming points is a subsonic flow, we could experience it to be you could consider this to be a complete nozzle till it comes out of till the fluid till the air comes out of this nozzle. That solves the problem. Now we can move to another set of multiple choice questions. It's a straightforward one. So this is regarding to the boiler mountings that are attached to the boiler. So in one of those previous questions, we have seen the accessories, what they do, how much they affect the efficiency. This is the mountings. So these are additional fittings that are being provided that ensure the safe operation of the boiler. So the answer is this one. They do not actually engage in the efficiency of the boiler. So mountings are basically they do not interfere they do not actually interfere in the performance of the boiler. They are only for operational safety. For example, a few examples of the boilers are water level indicator, pressure gauge, feed check valve, fusible plug that will melt once the load will be over a certain level. So, so these are boiler mountings and accessories. Difference is that boiler mountings are safe, are fittings that are used for safety purpose, while the accessories are something that improve the efficiency of the boiler. So the function of the fusible plug is to control the mass flow rate of the steam, to control the quality of the steam, to maintain constant pressure in the boiler, to extinguish the fire or decrease in the level of water level below an alarming level. So what happens is that when the water level goes below, there will be an overheating in the fire, overheating in the boiler, and that will be detrimental to the material that is used for making the boiler. So in order to prevent that kind of circumstance, when the water level goes below it, this fusible plug will melt. This is used in Cochrane type of boiler, fire tube kind of, not a water tube. The flue gases will be boiling through the fire tube in this case. Which of the following are the boiler mountings? Safety valve, water level indicator, steam stove valve, air preheater. So as we have seen in the previous questions, the boiler mountings are things that are used for safety purpose. The one which is used for improving the efficiency is an accessory. So a safety valve, water level indicator, and steam stop valve are the cases of boiler mountings. So this safety valve, once the pressure build up, it regulates. This is kind of a regulation valve. Once the pressure build up, it will automatically open. It will vent out the excess steam to ensure that the operation is safe. Water level indicator, just like the previous case, it is used to provide information to the fusible plug. As and when the level goes below, the fusible plug will melt, redirecting a bit of a steam that will be produced in this one. Steam stove valve also is used as a boiler mounting to prevent the steam from going out in certain cases. So this is an accessory. The function of the economizer in thermal power plant is to reheat the steam before entering the low pressure turbine. Preheat the air for better combustion. This is preheater, so it's wrong. Reheat the steam before it enters the low pressure turbine. No, that is so a reheater. Control the loss of steam. No, that's a steam stove valve. Heat the feed water using flue gas. X. We have seen in that question the numerical problem. Economizer is the immediate predecessor to the boiler, where the flue gas exiting the boiler will be used to preheat the water that will be coming out of the pump. So the boiler flue gas will be used to preheat the water in the economizer. So heat the feed water using the flue gas is the right answer. So that completes a set of problems I have for this week. So we have seen a few multiple choice questions and numericals based on the topics of this week: boilers, different types of boilers, superheaters, characteristics of convective and radiant superheaters, and the nozzles in steam power plant. So if you have any questions, you can post in the course website forum. We'll meet this Sunday with the next week's lectures due to a few numericals and multiple choice questions based on the next lectures. Okay. That's all. Thank you.